the recording.
So I'll be using a digital blackboard or whiteboard, not showing you a presentation. So
that's completely fine.
Yeah.
So thank you. And we'll today hear about magnetic monopoles from Samuel. So thank you for doing this, and the floor is yours.
Yeah. Thank you. So I'll do a very brief introduction into the theory of magnetic monopoles, focusing mostly on a single aspect that appeared in a research that I was doing 2 years ago. So the talk will be heading towards the result we got. From my point of view, sort of randomly, from the point of view of my back then supervisor, it was probably incidental, but okay, you can judge for yourself. So this, as you all probably know, these are the famous Maxwell.
Who was your supervisor again?
Peter Preschneider.
Okay.
Yeah. So, and we're studying something completely different. We're studying quantum mechanics in non-commutative space, but we found out that a certain generalization resulted into appearance of magnetic monopoles. And I will do this in a different context without the non-commutative space underlying the whole theory. Okay, so these are, as you all know, the famous Maxwell equations. So let me show you something that I like to call Max-Bedder equations. And these are Max-Bedder equations. They are better in a sense that they are more symmetric than the version that we are used to, that we know. And the interpretation of this modification is, well, this is a source of electric fields, so this is a source of magnetic fields. So this is something very well known. And well, the existence of magnetic monopoles has been considered many times, but always, well, it has been kicked out of the theory by the lack of experimental evidence. But still, well, we can develop the theory for magnetic monopoles, and there are still some clues that, well, we should be suspecting their existence. But also we know that if they really exist, they should be very rare and hard to produce in particle colliders and hard to find going through the universe. So basically the idea is that we have positive and negative electric charge. Then maybe we also can have like a separated north and a south pole of a magnet with magnetic fields escaping the monopoles and, well, not going anywhere. Now, we have built our theory of electromagnetism around the idea that divergence of the magnetic fields. So there are no sources. Probably because of that, it was figured out that, well, we can define a vector potential in a way that the magnetic field is rotation of this auxiliary field. And now when you plug in this expression, you get well, this is always zero. Now, if we would like to describe electromagnetism with magnetic monopoles, does it mean that we cannot use vector potentials as well? And the answer is no. The reason why those two operators are zero is basically there is a hidden something that is antisymmetric. In this is ijk times partial derivatives with respect to those two. So usually this is the same as in the reverse order. So we have something that is antisymmetric, and in this is ij something symmetric, so the result is zero. And this is coming from the fact that you can exchange the order of derivatives, meaning that but the truth is that you cannot do this anytime. If you have some kind of vector potential that has, for example, a line singularity, that then you cannot exchange the order of derivatives, and as a result, you will have non-zero right-hand side of this equation. So this is a very straightforward argument that you can still use magnetic potential, electromagnetic potentials to describe magnetic fields with sources, but you have to use singular vector potentials. So there is a very simple example. And when I was teaching electromagnetism, this was one of the homework problems to show that the rotation of this kind of expression actually gives you Coulomb-like magnetic field. I'm sorry for the messy equation, but well, this is the simplest form I know. And one of those is R, and one of those is a unity vector N. So we have a unity vector N, and along the vector, the field is singular because, well, this term is 0. And basically the homework problem was to prove that rotation of this A is G over 4 pi R over R cubed. So, okay, this is like the oldest version of the monopole theory, describing magnetic monopoles using
Can you go forward instead of just erasing what you write? I think it would be better to go forward in slides. Is it possible?
There is no slide. This is just one picture, but I can open another one and leave this one
Oh,
alive.
okay. So I thought it was continuous.
No.
Oh,
I'm typing, so I have to erase my Blackboard now and then, but I can.
Oh, okay. If it's too difficult, then never mind.
No, it isn't. But I'll have to be opening more screens and.
Yeah.
Okay. Yeah, of course, if you want to ask something, then it's nice to keep it alive. And basically, this is describing a field around a very thin semi-infinite solenoid. So the field is just escaping the solenoid, and from a far away, it indeed does look like a monopole. So these are magnetic field lines, and this is the solenoid. Now, so we can describe magnetic monopoles using a potential that is singular on a semi-infinite line. Now, the question is, can we do better? Can we actually describe monopoles without a singularity? So I'll just try to share a different screen now. Okay. And the question is that yes, that we can do it. But before showing how, I'll just stop by to say one important point. And it is that, well, the solenoid that we use to describe our line is basically artificial. In our expression for A, it depended on the position and on the direction of the solenoid N. But the resulting magnetic field depended only on the position. So So the position or the direction of the solenoid shouldn't be distinguishable. It's just an artifact of our description. But we know that, well, when you go around a solenoid, you pick up a phase. And the only way how not to be able to see the solenoid is that the charge of the monopole should satisfy a certain condition. And the condition is basically product of the electric and the magnetic charge should be, and I will denote this mu, this product. So it should be a half number. So 0, 1/2, plus minus 1. If this is the case, that by going around the solenoid, you will always pick up a phase of 1. So you cannot observe the solenoid, which is fine because it isn't really there. It's just artifact of our description. And this condition is called direct quantization condition. And it is one of the clues why to believe that
Did you say direct or Dirac?
Oh, Dirac.
Okay, Dirac.
Yeah. It's like American pronunciation of Dirac, but yeah, Dirac. Yes. And basically, if the product of electric and magnetic charge has to be a discrete number, then from it follows if there is a single magnetic charge somewhere in the universe, then the electric charge has to be quantized as well. And this is something that we do observe in the nature, that the electric charge of electron and of proton is the same, but the sign. And well, this may be the explanation for it. If there is at least a single magnetic monopole, then the theory tells you that their product has to be quantized. Okay, now let me move to a new blackboard. Share this one. Okay, now the question is whether we can describe it even without the solenoid singularity, magnetic monopoles. And well, the question is that the answer is yes, but we have to do a little bit more of work. And now this description was developed mostly by Young. And basically the idea is that, well, let me focus on a surface of a sphere. And you want to define electromagnetic potential for a magnetic monopole sitting inside the sphere. So one way you can do it is first take the solenoid to be coming from the south and use this to describe the field on the northern hemisphere plus a little bit below the equator. And you will get a potential, let me call it south. Now you can take another solenoid to be coming from the north. And now you can use this one to describe a singularity-free field everywhere on the southern part of the hemisphere, plus a little bit up the north. So in both cases, you are avoiding the singularity. But now you are using two different potentials. And around the equator, there is a line where both of those are active. So somewhere in this stretch between those regions, you can use both of them. And since they have to describe
Can I
the
ask a
same,
question?
yeah, sure.
So you're saying your a region where you define A north and A south and just before the equator, shouldn't
No,
it
they
be
overlap.
like a little bit after, so you have a non-zero overlap, and
Yes.
that would be the green.
So the red one is through here.
Oh, it's like that.
Yeah.
Oh, but then you would probably call that south.
Yes, but the solenoid is coming from the north. So
Oh, you take a south
Yeah,
pole
yeah.
magnetic.
yeah, it's messy. Sorry about that, but there's if I did it the other way, then it would be the same question. But yeah,
Okay, I understand now. Thank you.
Yeah. Actually, Sam, if I may go back one slide, I think in some sense, so I like much more what you're doing on this slide with where you're using neighborhoods and overlaps to describe. But in the previous slide, in some sense, one could, where you, do you still have access to the previous slide?
yes.
Oh, and the one more, I guess it was the first slide then. Do you also have that before where you
This is the first one I have.
Yeah, that one. In some sense, one could argue that that's not a true monopole because you need there's a direct string attached, and therefore the divergence is zero everywhere.
Well, yes, there is a string attached to it, but you get a monopole type of magnetic field.
Yeah, but you don't have a global description. That's the problem.
Yes, that is true.
I think actually I would dispute that you get non-commuting derivatives. I mean, the local description there's actually still there's still divergence free. It's just that we now give a new interpretation in terms of a direct string.
Yes.
Okay.
That I would describe as a sort of a historical approach.
Right.
Because there are many holes that this is leaking from.
Yes.
But basically the description of Young follows from this one.
Right.
And this is just a careful way how to describe it. So now we have two descriptions, no problems whatsoever.
Yeah.
Yes, I agree. And let me close this window. So, okay. Now, in the overlapping region around the equator, both of the descriptions are active, and well, they're describing the same field, so they can differ only by a rotation, by a gradient of a field. So they have the same rotation. So a north minus a south is it's a gradient of a function. And again, for example, if you are doing quantum mechanics, you'll get two types of solution expressed in terms of sections. So you will have a north solution, a south solution, and then there is an operator connecting them where this is I to mu phi. Again, now from the point of uniqueness of the description of psi, the charge has to be quantized. So when you go around the equator once, you pick up a phase of a 1. Now, well, people are obviously interested in physics of magnetic monopoles. They were believed to exist because, well, they very naturally complete the Maxwell equations. So they went to look for them, and actually the history is that magnetic monopole, a single one, is claimed to have been observed, and basically the date was 14th of February 1982, when people well, sort of measured magnetic monopole. If I recall the experiment correctly, they just make a very big loop, and well, if a magnetic monopole flies through it, that they pick up a magnetic flux, which generates some kind of a voltage in the system. And this is what has been observed, some kind of a jump. I think it was the other way around. And the date was 14th of February 1982, which is the St. Valentine's Day. So it's called Valentine's monopole. And it is now believed to be just a fluke. The experiment was rather new, so maybe some kind of a leftover of electric field or something like that. Okay, so people are trying to understand how to describe magnetic monopoles, electromagnetic fields around them, and so on. One of the important points is that if you have a system with electric plus magnetic charges, that the electromagnetic field has non-zero angular momentum. So then if you are, for example, doing something called monopole harmonics, which is like a monopole version of spherical harmonics, that the angular momentum starts from mu and goes up by 1 plus 1. And now if you study the algebra in the presence of magnetic monopole, then it's nothing wrong with the coordinates. Nothing wrong with this relation. But as it turns out, commutator of, now this one with indices, conjugate momenta is so presence of magnetic monopoles makes the underlying algebra a little bit more complicated. And this is a relation that I will recover later on from a very different point of view.
So I guess what you are drawing there is the kinetic momenta.
Yes, yes.
Not the canonical momenta.
And I will need to copy a new blackboard. Now, if you have never seen magnetic monopoles before, the impression you might get so far, it's always there is some kind of a circle involved. In the first case, we made a loop around the solenoid and checked whether we picked up a phase or not. In the second case, we made a loop around the equator. And in modern theories, monopoles are understood as sort of a topological defects, which sort of explain the discreteness of their existence, or discreteness of the Dirac quantization condition. And I will show just one very simple example, which I think was developed by Gerard Tuft, but I might be wrong about this. So if I'm wrong, please correct me. And basically, presumably he was analyzing SU2 gauge theory. And it goes like this. So
may I have a question before you make a new slide?
Yes, I made it already. I just didn't share it. Yes.
Yeah. What is R cubed? So what is R? Is it distance from monopole or?
Yes, yes, yes.
So this is distance from monopole.
Yes.
So the momenta becomes more non-commutative when you're closer to the monopole.
Yes.
Okay, good. Thanks.
Yeah, sorry for not not saying that.
And the monopole is at 0 somewhere.
Yes, it's sitting at the origin.
And the momenta pi are the regular momenta.
Yes,
It's the kinetic momentum.
kinetic. Yeah.
Because
M
with
times
kinetic
velocity.
momenta, it would be all right. The condition with the conjugated momenta, the true conjugated momenta, would be fine.
Would be 0. It would just be
Yeah.
0 in the
But
third. Yeah.
then it would be 0.
Yes.
Yeah.
Okay. Now, so Tuft and probably Polyakov as well. We're studying a theory, a gauge theory described by, well, let me do some kind of shorthand. So the usually field strength term plus. So it's a SU2 gauge theory with Higgs field phi. And the Higgs field is specified by a potential U, which is lambda over 8. The index A goes from 1 to 3, and V is just a number. And well, the question was, and let me just compactify the notes a bit. The question was, well, what are the vaqi of the theory? What type of configurations extremize the potential, the discrete extremize the action? And well, one of the obvious solutions is, well, you can just take phi to be constant, take the gauge fields to be constant or 0, and the constant of phi is defined by the potential to be, well, a square root of V. Well, but the question is, aren't there some kind of, well, fancier vaqi? And the question is, yes, there are. And basically, the idea is you have 3 fields phi, and together they have to be living on a sphere. Now, without going into details, you can specify the vaqi of this theory by specifying their boundary conditions in the space infinity. So you have to specify the value of phi's in the spatial infinity. So this is x, y, z. And now the spatial infinity has the shape of a S2 sphere, which is, well, with the infinite radius. But you have to specify the boundary conditions on a sphere. And on each point of the sphere, you are free to choose a value that is also living on a sphere. This is describing a sphere. So for example, here on the equator, you can take phi as a vector to be, I don't know, 0, V, 0. Here on the North Pole, you can take it to be 0, 0, V. The only condition is that for points that are very close to each other, the boundary conditions should be nearly the same. It doesn't have to be the same condition, but an infinitesimal change in the condition between infinitesimally close points. So basically the idea is that to each point on a sphere, you are mapping a different sphere. And now there are non-trivial ways how to do it. For example, let me just take the great circle. So for example, on the North Pole, you can take the field to be pointing this way. And this is called the hedgehog solution because, well, this looks like a hedgehog to some people. Not sure how to draw a hedgehog, but it's basically the idea. And the thing is that you cannot deform this solution smoothly to the trivial solution. The trivial solution is the same arrow everywhere. Without crossing infinite energy barrier. So for example, if you would try to start aligning this, that you can align this, align this, align this, but then this one will be the other way around. So there is some kind of a cusp you need to cut and reconnect it again. And actually there is a integer amount of ways how to do this. So in the first non-trivial example, when going around the great circle, the arrow turned once. That you can have the arrow turning the other way or turning twice, 3 times, 4 times, and so on. And well, a non-trivial way is to show that this kind of solutions produce something generating monopole fields. But also this is underlying the topological aspect of monopole solutions and their discrete nature. There is a discrete amount of ways how they can be produced.
Samuel, is it the classification of sphere bundles over a sphere?
Yeah.
Yes, exactly.
Or is it? Yeah. Okay.
Yeah. And in the previous case, it was basically the homotopy group for the mapping of a circle onto a circle.
Yeah. Uh-huh.
So you go around a circle, you have to end up in one, but well, you can loop or wind around the loop any amount of times to reach one.
Thanks.
Okay, let me get to a new blackboard.
Can I ask a question about this slide before you go?
Yes.
So I don't really see how this is related to the monopoles because there's no like electric field, magnetic field. It's just like a topological defect. So I guess you could call this an instanton or a soliton or something like that. But is this like a more general property that you want to talk about, or is there some more concrete relation to the?
This is a gauge theory. So through the kinetic term, this is coupled to the gauge field, and the gauge field now then has a form of a monopole potential.
Okay, yeah.
But it's just a slight sidetrack because, well, a different reason why the monopoles have a topological structure. Okay, let me find my blackboard. Sorry. Okay, I got it.
Right, but maybe we should stress that gauge potential solution is actually regular everywhere in 3 space, unlike the Dirac monopole, which only is finite on a punctured 3 space.
Yes. If I understand this correctly, this sort of regularize the monopole. It's like it isn't located at the origin, but it's like blurred around the origin a little bit.
Yes.
So if you try to remove it, you will sense its presence sitting at the origin, but not exactly there. But well, this often appears in the lattice context. And in the lattice context, the monopole usually is sitting on a single lattice node. Okay. So now finally we are getting to my research. If you're interested, I will give you the archive number for it, and the archive number is it's quant. quant and 104040015. And now the name of the paper is, or the title is Alternative Description of Magnetic Monopoles in Quantum Mechanics. What we are doing is that we used different descriptions of quantum mechanics, as is usual, because, well, it was for the purpose we needed it for. It was more convenient, but it will give you the impression that we are stretching we are scratching our left ear with our right arm. So it seems like doing the same work in a more complicated way, but I'll show that it has some kind of benefits. Okay, and basically the idea is that, well, usually quantum mechanics, as we know them, are living in our three-dimensional space, and we describe, so I'll just close this window. There is a hockey player practicing every afternoon. Okay, so usually we describe states of particles in quantum mechanics as some kind of functions of points in three-dimensional space, and we require those functions to be square integrable and so on. And now this comes equipped with some kind of algebra. So for example, XX PP is 0. This and this one. And we require psi squared either to be 1 or to be, well, not infinity. Okay, now there is a sort of a cousin, a larger cousin to our space R3. And this is the space of two complex dimensions C. The reason why those two are, well, somehow related is, well, basically the algebra of rotations here is SU2, which is close to SO3 in the three-dimensional space. Here you have two complex coordinates. Let me call them Z1 and Z2. And basically, well, you can start thinking about wave functions living in this complex two-dimensional space, function of Z1 and Z2. Now, in principle, this will give you a different type of quantum mechanics because there are more functions that there are in three-dimensional space. But there is a special class of functions that can be mapped here. And well, this can be done in the case if you are considering functions of this form, or x, y, z bar. This is the Pauli matrix times z. So if you are considering only functions of this form on the left side, then those can be mapped into the functions of the right side. Now there is a very simple way of how to see this. There is a way how to parameterize the two complex dimensional space using Euler angles, which is r cosine of theta over 2 times exp of I over 2 And Z2 is the same, but with sign here. So there are some kind of spherical coordinates that you can use in the complex space. And now if you make combinations of them using the above mentioned equation, that is x is z bar sigma z, then they will exactly result into x, y, z expressed in spherical coordinates. So for example, in this case, it will be z1 bar z1 minus z, giving you the third coordinate, which is, well, z.
Let me just.
Samuel, cannot one say that if I have a three-dimensional sphere in a C2, then I
Yes.
can map it with a stereographic projection to R3. That's the same, I think.
You can do something that is called a Hopf vibration. So
Yeah,
you can
that's
have.
it. It's a yes. That's well. That doesn't give me the whole of R3, but
In this case, this gives you everything.
yes. Well, one can rather say that I can map the whole of S3 to the whole of R3 by stereographic projection, right? You want to map to the whole of R3, right?
Well, what you can do here is that you can, in both spaces, you can set up sort of spherical coordinates, but in one case you are using three-dimensional spheres, and in second case, two-dimensional spheres. And now you are mapping the sphere onto a sphere by losing a circle.
Yeah, I know the whole vibration. But well, and the sphere S3 you are using because it's an orbit of SU2, right?
Yes.
You can kind of peel the space C2 into different orbits, and each of the orbits can be mapped to R3.
Yes, some kind of a onion structure.
Yes,
Right.
that's it, I think.
Yeah.
Okay, so in the exponential, this is a theta and a phi.
Yeah, I'll just write it right here. So we have.
This is theta minus phi, right? Or what? I cannot read.
It's gamma. I will just write
what is
a
gamma?
nice. So here you are using 4 coordinates: r,
okay.
theta, phi, and gamma.
Gamma.
And here you are using r, theta, and phi only.
All right. And your var phi and your phi are the same.
I hope
that's
so.
a theta. Oh, that's a theta. Okay, that's a theta.
Yeah,
All right.
yeah, that's a theta. Sorry for my terrible handwriting.
Yeah, it's okay.
Yeah. Okay, and what has been lost in the translation is basically this angle gamma, which this entire angle is being mapped into unity. So we are losing a circle. So again, it feels like there is some kind of a monopole structure looming behind, or there is some kind of opportunity for it. But it still isn't clear, well, where is it exactly sitting? So I'll share another screen. Am I sharing? No, not resume share. Okay, I am now. So Now we are sitting in C2, considering only special functions of this form. And now there is another benefit of this space, that it comes naturally equipped with a Poisson structure. So we have Z star. Z alpha beta is, I think it's minus here, not really sure, and it isn't really important. And the rest of the Poisson brackets is 0. So therefore you can very naturally define second order operator acting on phi, where this R is Z alpha Z. Now, if you try to do this, we will find out an interesting thing, that if you are working only on functions of the form phi r, that this will exactly look like ordinary Laplace operator, which is taking double derivative with respect to. So it's basically mimicking the ordinary quantum mechanical operators we know. Again, using those operators, you can define the momentum operator, which will act the same way on those special functions as before. So in principle, you can do whatever you like. You can do entire quantum mechanics on C2 instead of doing it on R3. There are minor differences. For example, the integration is, well, there is a factor of R to reproduce the ordinary quantum mechanics. So, and so on, but those are just minor differences. Also had to plug 1 over R into this operator to get the same result. But in principle, if you want to make your life complicated, you can do quantum mechanics on C2 instead of R3. And now, well, the question we ask is, what would happen if we considered a slightly more general state? So instead of using just a state of the form psi as a function of this combination, let us add something a little bit extra, something where psi of k is, for example, this would be psi 1, I think. So you take something that can be expressed as a function of x, y, z, or as 3 Euclidean coordinates, and then you add something that cannot be expressed. So in this case, the result still depends on the coordinate function of r, theta, phi, and gamma. Still depends on the spatial angle. And well, in general, we can take some kind of combination like Z1 over Z1 star.
Okay.
where this goes to k minus delta over 4. And the same with Z2. And this star Z2. This now with k plus delta. And we asked the question, what would quantum mechanics with those kind of generalized states look like? And well, as this is a talk or presentation or seminar about magnetic monopoles, then you can probably figure out the question, the answer. And the answer is that this exactly describes a quantum mechanical theory with magnetic monopoles of strength mu is kappa over 2. Now in our case, kappa was a whole number, so mu is a half number. So basically exactly the Dirac quantization condition. Well, what do I mean that this describes quantum mechanics with magnetic monopoles? So for example, we can take the angular momentum operator and find out that this develops a contribution even for a static system. Then, for example, commutator of peace is kappa over 2 and actually we can see that this splits into two contributions. One is an ordinary derivative plus something that looks like a gauge field. And if you compute what is the rotation of this gauge field, it's exactly minus kappa over 2 plus xy over R3. And there are, well, more signs that we are observing magnetic monopoles, but this should be sufficient. So the bottom line is that we found out that if you make your life harder by describing quantum mechanics on C2 instead of R3, there is a simple way how to include magnetic monopoles in your theory. And well, the way how to do it is, well, consider a slightly generalized class of states. And this is the most general solution that depends on k, which is a whole number. And there is extra choice of delta that, however, always can be gauged away. So you are feel free to pick, for example, delta equal 1 or minus k or something like that. And as a result, we got the exact monopole algebra. And by the way, the reason...
The commutator there, that's just the Poisson bracket, right?
Yes.
And that Poisson bracket is the same Poisson bracket as you had in C2.
Yes.
I mean, it's induced from C2.
Yes.
And is it true that the Poisson bracket on what's it called position? I mean, so then, I mean, if you write the X, Y, and Z in radial, I mean, then you just get the ordinary what you call epsilon tensor for the Poisson bracket also there. Is that true?
I'm 99% sure that yes.
Yeah.
And just by the way, the reason why we're interested in this approach is that we are studying non-commutative space. that you can simply do by quantizing C2. That is basically, you can replace this relation with a commutator. That is Z plus this.
Right.
Yeah. And then you can, well, represent the coordinates using oscillator operators, a set of 2 of them. And then you have quantum mechanics expressed on a non-commutative space. So we did this in the reversed order. We are doing quantum mechanics on a non-commutative space. We were analyzing, for example, what are the solution to the hydrogen atom problem and how are they sensible to the underlying structure. And then, well, we got some kind of class of solutions, and then we tried to figure out what happens when we try to generalize this class of solutions. And we found out that, well, the algebra gets more complicated. We get some kind of new contributions, but they seem to have some kind of a structure. It wasn't like completely random corrections or something like that. And then like doing reverse engineering, unquantizing the theory in the C2 space and looking what is this really describing. So then we figure out it's magnetic monopoles. Okay, so this is the end of my talk. Thank you for your attention.
Okay, thank you very much. So I guess we can start the session for questions and comments. So if you don't mind, I'll just begin with one simple question. So you have this Hopf vibration from C2 to R3, and previously where you were describing these magnetic monopoles, you always had some, as you said, some circle which would give you the direct quantization condition. So in this case, I guess, can I think of the fiber of this one circle that you lose or that you get extra in the C2 case of this this thing which helps us get the magnetic monopoles, as in your previous cases you always had something like that.
Yes, exactly. Basically, you can even, if you expressed what is the extra factor that I added to the solution, it's just e to the I gamma, like the extra circle. So exactly, you are providing the theory extra circle to wind around.
Okay, yeah, that makes sense. But I guess you could do something like you forget about this C2 altogether, and you can just write down the algebra for the monopole in your R3 space, and it would sort of seem like something unnatural that you just add some right-hand side which is non-zero. But this construction, it shows you how it can arrive from some higher structure. So I guess it would give you like a geometric interpretation of what could happen.
Yes, exactly.
Okay.
Yes.
Yeah, that's good. Thank you. Yeah. Okay. So some other questions, please.
Can that extra circle be identified with some phase factor in the Hilbert space of the wave function or something?
Yes, and I'm always thinking like this is an interesting aspect of electromagnetism in general, that the gauge theory is a very simple space. And for example, if you have the Kaluza-Klein theory of joining electromagnetism to gravity, they also did like an extra circle to the 4-dimensional space-time. And then the question is, well, can you think of all gauge symmetries as kind of like extra spaces living somewhere? Not sure about it, but at least in the simplest example, it's, I guess, perfectly fine.
So are there any other questions or
I
comments?
have a comment.
Yeah.
I think this trick with the z's, like when you use this vector of z bar and then the sigma matrices and then the z, well, you obviously, if you have a longer vector, you would have to use some other matrices, representations of some Clifford algebra. But this was done, I think, for these sigma matrices. It was done by Julian Schwinger in his theory of angular momentum
Yes.
monograph in the 50s. I think it's an old trick and very, very smart one.
Yes.
And he also he basically used harmonic oscillator relations for figuring out a lot of things about angular momentum. This is very useful.
Yes, yes, yes.
So that's it.
Yeah, thank you. And there is one name I also wanted to mention, and I completely forgot, is Zwanziger, who developed huge parts of those theories. And he was involved in the classical theories of monopoles, but also in, I think, in quantum modifications. I'm not sure about that. And he was focusing on particles called dyons, which is a particle with both electric and magnetic charges. And one point
I think
yeah.
he's at NYU, Zwanziger, New York University.
Okay.
Anyway, but he must be retired by now.
Yes, the paper by him was 1968, I think.
Yeah.
So yes, I would say he's been retired already. One point is that in the 't-Polyakov theory, you can, well, you can connect the mass of the monopoles to the breaking of GUT theory, grand unification theory. And when U2, U1 group singles out, then when the monopoles are expected to be produced, which, if this is the case in our universe, they should be very heavy, which explains why they haven't been observed in particle colliders, but they might have been produced early in the universe. And the inflation theory, one of the results it's known for is that it solves the monopole problem by, well, diluting the monopoles throughout the universe. So if they exist in the nature, they are very scarce.
Do you know if there are some ongoing experiments trying to find out some evidence of monopoles?
I'm not sure. I would be surprised if not, because, you know, just have a loop somewhere in your basement and for the result. But I've seen some.
So are all the experiments of the form as you showed us in the Valentine's Day that you are trying to pick up some current from a closed loop?
I think so, yes. Maybe I'm wrong, but this is the only one I know of, and I can share you the screen.
Yeah, I think I mean there is some kind of topological condition that have to be satisfied for gauge theory to have monopoles, which I forget right now. But I think the point is basically that if you are given a gauge theory with Higgs field and so on, I mean not necessarily SU2, but maybe some other gauge group, then you know just from then the theory, because you're just asking for what are classical solutions. I mean to your theory. I mean classical, not what's the word? Non time dependent solutions. I mean in static solutions,
Static.
that is just a matter of whether you can. I mean that you, in some sense, you don't have to make any experiment because that just comes out of the theory. So what you need experiments for is just to figure out what theory you're talking about. But once you know that your Gates, your good theory is such and such, then it follows from the theory whether there's magnetic monopoles or not.
Yes.
Of the 't Hooft Polyakov type. So, but of course, it would be nice also to see it experimentally. But it's a fact just buried in which theory we are talking about.
And I just quickly checked that, well, Atlas collaboration in CERN published a statement about new result in hunt for mysterious magnetic monopoles. So people are still looking for it, but well, the result wasn't a successful find. It was just, and this is the, I'm just sharing the screen with the Valentine's monopole. So 1982, not 86. So, well, it would be an irony if this indeed was a magnetic monopole that was discovered briefly after the experiment just went online, but we cannot conclude anyway.
Maybe we should also say that there was 2 or 3 years ago, there was some people who claimed they have seen magnetic monopoles in condensed matter, but that was synthetic magnetic monopoles. It has nothing to do with these fundamental ones.
Yes, you can make something that looks like a magnetic monopoles from far away, but that's not a real magnetic monopole.
Okay, so are there any other questions? I guess I should have stopped the recording already, but in this video we will have also included the question section.
Yeah, that's fine.
Okay, so if not, then